Assalamualaikum. We are from Group I from Computer Organization and Architecture. Our presentation topic is Intel 86 Memory Management. First and foremost, let us introduce ourselves. My name is Nurul Izzati binti Azizan and my matric number 060299. Thank you.
I am Nur Syuhada binti Abdullah. My matric number 060544.
My name is Adiawanti Anwar. My matric number is 060548.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amin bin Zakaria. My matric number is 059230.
I'm Muhammad Hafiz bin Abdullah and my matric number is 058994. Thank you.
Let's get to know what is Intel x86 memory management. Roughly, Intel x86 is a family of instruction set architectures initially developed by Intel. Many additions and extensions have been added to the x86 instruction set over the years. As of 2021, most personal computers, laptops, and game consoles sold are based on the x86 architecture. So, back to our topic, we have three things to talk about regarding Intel x86 memory management. First is segmentation. Segmentation is one of the ways to access the physical memory. When Intel first designed x86, it had an idea that every memory item would be in a segment of memory. Each segment was a small chunk of memory of a specific size. Next, we will discuss about paging, another way to access physical memory. Instead of memory being divided into segments, it is divided into pages and frames. The last one is protection in memory management, which to prevent a process from accessing memory that has not been allocated to it. This prevents a bug or malware within a process from affecting other processes or the operating system itself. Okay, we will look at this figure first. This is only a brief introduction about the differences between segmentation and paging. We will go further later. As you can see in this figure, segmentation using logical address while paging using linear address. As I mentioned earlier, each segment was a small chunk of memory of a specific size. So each segment would be serve different purpose. CS, code segment, would be used to store executable code. Default segment, DS, would be used to store data. Stack segment, SS, would contain stack information. Extended segment, ES, would be used for whatever programmer intended it for. Later on, the portfolio of segment registers was extended to FS and GS. These ones don't have a processor-defined purpose, but programmer can choose what to use them for himself. In the end, modern x86 CPUs have the following segment selectors: CS, DS, SS, ES, FS, and GS. While each segment descriptor is itself stored somewhere in memory along with all the other segment descriptors. For instance, when an address being fetched, it will goes into segment selector. Then, segment descriptor will store the memory.
Hai, Assalamualaikum warahmatullahi wabarakatuh.
I will briefly explain about x86 memory segmentation. First of all, what is segmentation in memory management? Segmentation is a memory management technique in which each job is divided into several segments of different sizes, one for each module that contains pieces that perform related functions. Each segment is actually a different logical address space of the program. So, x86 memory segmentation refers to the implementation of memory segmentation in the Intel x86 computer instruction set architecture. Logically, in order for the system to be able to derive the actual memory address, there will be a certain needs. The Bus Interface Unit (BIU) contains 4 16-bit special purpose registers. The first one is Code Segment Registers (CS). Next, Data Segment Registers (DS). Next, Extra Segment Registers (ES). Lastly, Stack Segment Registers (SS). All these registers takes place in a memory. Code segment registers is used for addressing memory location in the code segment of the memory, where the executable program is stored. Data segment registers points to the data segment of the memory where the data is stored. Extra segment register also refers to the segment in the memory, which is another data segment in the memory. Stack segment registers is used for addressing stack segment of the memory. The stack segment is a segment of memory which is used to store stack data. Okay, so now maybe you are wondering why must we use segmentation in the memory management. To answer it simply, segmentation are used because of several useful advantages. Firstly, it provides a powerful memory management mechanism. Next, it allows processors to easily share data. Last but not least, it allows the extent of the addressability of the processor. For example, segmentation allows the use of 16-bit registers to give an addressing capability of 1 MB. Without segmentation, it would require 20-bit registers. That's all from me. Thank you.
Assalamualaikum. Today I want to talk about Intel x86 architecture, which is segmentation, global and local descriptor table. Okay, first I want to explain what is the segmentation descriptor. In memory addressing for Intel x86 computer architectures, segment descriptors are a part of the segmentation unit used for translating a logical address to a linear address. Segment descriptor describe the memory segment referred to the logical address. In addition, segment descriptor also is a data structure in global and local descriptor table that provide the processor with the size and location of segment as well as access control and status information. This is an example of segment descriptor. Next, I want to explain about global descriptor table. The global descriptor table can hold things other than segment descriptor as well. Every 8-byte entry in the global table is a descriptor. These descriptors can be referenced not only to memory segment but also to task state segment, local descriptor table, or call gate structure in memory. The last one, call gates, are particularly important for transferring control between x86 privilege level, although this mechanism is not used on most modern operating systems. Then, local descriptor table is a memory table used in the x86 architecture in protected mode and containing memory segment descriptors. Just like the global descriptor table addressed in linear memory, size, executability, writability, access privilege, and actual presence in memory. There is also multiple local descriptor tables can be defined in the global descriptor table, but only one is current at any one time, usually associated with the current task. While the local descriptor table contains memory segments which are private to a specific program, the global descriptor table contains global segments. The x86 processor has facilities for automatically switching the current local descriptor table on specific machine event, but no facilities for automatically switching the global descriptor table. This is example of global and local descriptor table. That's all from me. I hope everyone understand and thank you for taking time to listen of my part. Thank you again.
Next, we will discuss about pegging. As Juhaida mentioned earlier, pegging is a different way of accessing physical address. Virtual memory uses this as part of the memory. Those memory sum of all programs can be larger than physical memory. Only part of a program must be kept in memory, while the remaining parts are kept on disk. So we need to remember this, okay? The memory used by the program is divided into small units called pages. Okay, before we move, let's get to know the advantages of pegging. First, using pegging allows us to create arbitrary memory layouts and better utilize memory. Second, pegging allows us to implement more complex scenarios where each process has its own address space. I hope you can see this picture. This picture is about linear address to physical address translation, or we just say page translation. Okay, what is page translation? Page translation is when CPU convert the linear address to physical address. Based on this picture, linear address is divided into 3 pages. First, page directory field, second, page table field, and third, page frame offset. For your information, the CPU uses all these 3 pages to calculate physical address. Now I will explain on how pegging works. As you can see on the screen, there is typical main memory, RAM, secondary memory, HDD, and CPU. The size of RAM is limited compared to secondary memory. Okay, let's say there are a lot of applications running in the RAM. When we open up more complex applications, they take up more RAM and more processing. In this scheme, we use some portion of secondary memory as a virtual RAM. It can be used to store processor in terms of pages. So this pegging scheme is being implemented by Memory Management Unit (MMU), which is a unit inside data system which basically perform and apply this pegging scheme. Okay, what happened here? Some part of the running application can be stored in the secondary memory if they are not used. So CPU gonna be running some other processor application. I hope you understand what pegging is and how pegging works in Intel memory management.
Next, we go for protection in last process of Intel x86 memory management. And protection it will be true for privilege level checking, which is the segment protection mechanism recognizes 4 privilege level. It is numbers from 0 to 3. After addressing from linear address to physical address. The greater numbers from the privileged numbers will be assumed as lesser privilege and not going to be in segment protection. So basically, the privilege levels are organized something like on the diagram. Privilege level 0, PLO, correspond to kernel mode, while privilege level 3 correspond to user mode, and privilege level 1 and privilege level 2 correspond to system service. When When performing privilege level checks to see if a particular segment is accessible as a data segment, the processor must decide what the current privilege level is and if that level is privileged enough to access data segment. Privilege level are used code modules in lower privilege segments can only access modules operating at higher privilege. Segment by means of a tightly controlled and protected interface called gate. So, what is gate? Gate is defined as a set of special descriptors called gates, which is called gate, interrupt gates, trap gates, and task gate. These provide protected gateway to system procedures and handlers that may operate at a different privilege level than application programs and most procedures. Privilege levels are checked when the segment selector of a segment descriptor is loaded into a segment register. This shows that every levels will be checked to collect that privilege levels. So when the processor detects a privilege level violation, it generates as a general protection exception, which is GP. To carry out privilege level checks between code segment and data segments, the processor recognizes the following three types of privilege levels, which the first one is current privilege level, which is CPL. CPL is currently executing tasks, which means the code segment from every instructions are being fetched and collected. Second one is descriptor privilege level, which is DPL, which to be added as level of segment of gate. So at this stage, every code segment will be checked to enter the gate. And the last one is requested privilege level, RPL, as an override privilege level that is assigned to segment selector. As overall, privilege levels are used in protection are to make OS system run smoothly and well. When privilege levels are at the high privilege, user can do anything to reach for the OS kernel, but when it comes to low privilege, the limitation and less useful for user, which is it used to application programs and protect other modules and kernel from the application program. So that's all from me. Thank you.